Shatak is commenting, glad to be here. Welcome, Shatak. Great to have you here.
Hi, Martin. Thank you. Thank you so much.
Yeah, welcome. And everybody who is attending on a mobile phone or a tablet, just make sure you don't touch the screen because that kind of draws on my screen as well, so it gets really weird. So let's continue with the meeting then. Today we're going to be talking about higher level design patterns in C. So when we're coding embedded applications, you can find a lot of information on the C programming language. So there's a sea of information. You can find almost everything related to the C programming language. But when it comes to design patterns, that's where the information is scarce, and you have to kind of study existing projects to find the valuable things. Like, how do you structure your code? How do you make sure that your code is maintainable? How do you make sure that your code is prepared for things like being able to split it up into multiple threads? And all of those things are part of what I call the higher level data, which I think it's important to learn the higher level data, because everything else fits into it. It's like a framework into which you can fit everything else that you learn about the C programming language. So when you learn about arrays or memory allocation or structures or pointers, it kind of all fits into this structure of design patterns that define the way that we structure the code at a higher level. And it's kind of like in programming, but also in the universe in general. We have this idea of a fractal pattern. So things that are on a smaller scale, they repeat themselves at a larger scale and the larger scale and the larger scale. And it works kind of the same way in programming as well, where you have at the highest level, you have your application, basically, what are we trying to do as programmers? We're trying to create a binary image that is going to run on our processor or run as an application on our computer. And we've been trying to do this since 1972. It's like it's what we basically do at the highest level. And the binary image is basically three types of arrays. We have our code, we have our data, and we have our uninitialized data. And everything we do in the C programming language is kind of arranging things that then fit into these three main types of arrays, which constitute the structure of the executable file. We have the executable and linkable file format that is used to store our program data. Whenever we work with embedded applications or just applications in general, everything that we write in our code compiles into a container that we call the ELF file, which contains our code and our data. At the highest level, like when we are developing the embedded application, what is it that we actually have? Well, we have the ELF file format. So all programs are split into a number of different sections. These sections are then mapped to run at specific addresses in memory. So when we start developing for a new chip, we look at the datasheet for the chip, and we look at where the flash memory is located. And then in our linker scripts, we define that we want to put code into location 0800 0000, for example, which would be the start address of the flash. That's where our text section goes. So all the code that we then compile goes into that section. And then we have the initialized data section where we group together all the variables into one big array, all the variables that have values defined, and we just compile them into this array. And this array just gets loaded as is into the RAM memory on the chip that we're working on. The compiler just takes all the variables from everywhere in the application, everything that has that is a global variable with some kind of value assigned to it, and just groups it together into one array that we then can load at startup time into RAM memory. And everything that doesn't have any values from the beginning it gets grouped together into the BSS section, which contains all the uninitialized data. So The BSS section gets just zeroed at startup. And so when our application, when our ELF file is either loaded by a bootloader as just directly, so a bootloader can typically read an ELF file and just extract data out of it and put it in the correct locations in memory. Or we extract the data, we discard the container, we extract the data as a binary file, and we just flash it into the chip, which we typically do on microcontrollers. So when we flash the flash memory in the microcontroller, we take the data directly out of the ELF file and just put it directly into the flash. But whichever way this happens, the microcontroller is then starts the execution in the text section. And we want to structure our program in such a way that we can sort of understand it better and keep track of all the parts, all the moving parts of our program, and not get confused with where things are changed and how things are changed in our application. And to do this, so let's see, we can also go quickly here through the firmware. We have the bootloader, we have the main program that gets loaded by the bootloader, and we have the application. When our application starts, we basically just load the address of the reset vector and start the application. We use the C language because it maps so perfectly well into this structure of the program at the lowest level, at the CPU level. So in C, we group our data into structures, and those structures then directly become the parts of this arrays of memory that we have in our executable container file, and also then in the memory of the chip. So the reason that we are using C programming language is because it's the language that most directly maps into the structure of the executable file as a whole. And so why don't we just code in C then, and just sort of write in whichever way we want? Well, that's what we start as. That's what we do, like when we start learning the programming language. But then we quickly discover that it's not enough to just learn the programming language. You also have to understand how to structure the code. And so that's why we have higher level design patterns for the source code, and for it's kind of like unwritten rules that are not enforced by the compiler, but the rules that you decide to follow by yourself in order to make your code easy to read and easy to extend as well. And I'm going to be outlining some of these rules, and we can look at examples as well of how these rules can be used. So one of the most basic rules in C is that you want to try to keep your data grouped together. So there's one place where you define your structure, but also you then have the instances of that data. And most people don't think one step ahead, and they don't think about instantiating their data. So when you have global variables, for example, in your code, you are instantiating those variables one by one. What you want to be doing instead is defining them in a structure so that you can instantiate multiple copies of that object. If you need more than one copy, or even if you don't need more than one copy, it's still a very good idea to kind of group things together and not just let the variables be wherever you place them in the source code. So rule number one is to put all data into structs. Like, you never want to have any global data at all. The only global data that you should have, or that you ever have, you don't even need to have that. But if you're going to have any global data, then it's just global accesses to registers and things like that. So you have variables that point to resources on the chip, where you access the UART, for example, and you have a structure that is a global structure with an address, fixed address, that points to that UART. And that's the only global stuff you need. You don't need any other global data. Everything else you would place into structs. And so in C, C is a very simple language. So it doesn't have any advanced concepts when it comes to objects. Like it doesn't even have object-oriented design built into the language. It's something you have to design around. You kind of design your own object-oriented approach with the language. And an easy way to understand how to work with C is that in C, you have structures, which are structs, that's your data. And then you have methods, which are the behaviors that you want to apply to that data. So you put your data into structs, and then you have methods that operate on that data. And what this means that your methods will always take an argument, which is the equivalent of this pointer in C++, but in C, you do that explicitly. So the first argument to your methods is always going to be some sort of a self pointer. So it's going to be called self, and it's going to point to a structure where you have your data. And when you do it that way, you take this, you take all the side effects out of the function itself. So if you were to define things globally, so if you were to have global state in this scenario, and then your function is accessing global state, then you suddenly have lots of different side effects. So you can have one function that accesses part of the global state, and then some other function accesses another part of the global state. So you end up with this scenario where you don't know where the changes are coming from. So anywhere in your code, something can change your global variable and you wouldn't even notice that. Or it's like, even if you're debugging, you have to set a breakpoint on access to that memory location to even see where it is changed. What we're trying to do with the struct pattern is to take control over the data flow in the application. So you have you make the data flow hierarchical. So your data flow is always through the call graph of the application. You start at main, that's your main entry point. And then from main, you have data that you pass through the code wherever the data is needed. And you don't pass too much data. You group data into structs, so that you just pass whatever is relevant to a particular object, a particular part of your application. So let's say you have a dictionary where you store some values. That would have its own variables that are used to store the data in the dictionary. And you can have multiple instances of that dictionary. So you would have multiple members of that dictionary in your application struct. But even your application struct is a structure. It shouldn't be any global variables defined in your main file, main.c. It should just be at the very, you can have a global application structure, but not individual variables. So you would put everything into one big application structure. And from there, it's kind of like a tree. And so when you do it this way, your data flow is always through code and not outside of it. And this is an important feature that's going to make your development so much easier, because when you know your data flow, you always know that whenever you pass this object to a function, if the function is taking a pointer that is, let's say, you're passing a pointer that is const to that function, you know that that function is not going to change that pointer. And even if you're just passing a pointer to a structure, you know that, okay, I'm passing this pointer, so I'm temporarily giving away ownership of that pointer. And then that function may change this pointer, so I have to be aware of the fact that maybe it's going to change some data in this object. And then I can continue using that pointer when the function returns. As opposed to, like, if you were to, when you look at how most applications are made, you have this global state, and then functions just change things at random, and you never know what have they changed. With this approach, you know exactly that this is the only data that the functions have access to, and they're not going to change anything else. So that's really powerful. And that comes in handy when you then start adding multi-threading to your application, because now everything is just naturally, it's naturally reentrant, because you can have multiple code paths calling the same function, and it's not going to have any side effects because you're passing instances of the self object to those functions. So you don't have to worry about any external side effects that those functions might have. So that's really valuable. And how does this actually work in practice then? So, for example, I have the MCP 4461 device driver. I define this instance. I define a structure that defines the variables that describe this device driver. So naturally, it needs to have a handle to the I2C device. It needs to have access to GPIO. It needs to have its I2C address. It needs to know which is the reset pin, the write protect pin, and it also needs to have an analog device interface exported outside of this instance of this object. And this is an I2C potentiometer. So this chip is sitting on an I2C bus, and it's basically a controllable electronic potentiometer. So you can use it as a normal potentiometer, except that you're controlling it over I2C. So you can set values on it over I2C. Whenever I need to use this device, or whenever I need to use this object of MCP4461, all I have to do is just pass an instance of this object to whatever functions that I use in it. So for example, if we have a write register here, this function is defined as local function. It's a helper function. So we define it as static function, not exported outside of the C file. And we pass the MCP4461 as a self pointer, as the first pointer in the function declaration. So we know that everything that this function does is going to be done to this object. There's nothing else. There's no other side effects. So this is an written rule you have to follow for yourself. It's not something that the C language is going to enforce. So it's like, if you don't know about this, you're going to just naturally make mistakes. But if you force yourself to follow those rules, then everything becomes really, really simple to grasp for yourself when you're writing your application. Your application becomes really much more maintainable, and it's just easy to add, extend, and whatever. The other two arguments are uint 8 arguments. So I always use sized integers when I pass values, because it just makes sure that it's clear that these variables are 8-bit range. So they're not, they can't contain any values outside of that range. And then we just construct sort of here the packet, and we send it using an I2C transfer. So we know that from this declaration of this object, from this definition of this object, we know that it has an I2C device. So probably it's any function that takes this object as a parameter, probably going to access the I2C device, probably going to access GPI device, probably going to do something to the internal variables, but nothing outside of that. And this is really powerful. Because what can we do now? Now we can easily take this file, we can compile it as a standalone C file. We can link it with a test suite where we instantiate an instance of the MCP4461 object, and we can actually then pass this instance to the code, and we can test the code that way. We don't need to have we don't need to worry about mocking up like all the global local variables that this or especially extern variables that a C file needs to access. We have everything contained in our structure, so we can easily mock it up and then pass it to the code to test the code. Unit testing becomes really a lot simpler with this approach, and it's just like there's just so many benefits. So one of the most important design patterns, I would say, to use in C is to put everything into structs. If we take it one step farther, we can also have hierarchical containment. So if we start at the highest level, we group things into structs. We can then have smaller objects that are also part of the bigger struct. And everything becomes really clear then. What is it that we have in our application? What data do we have in the application, and what is responsible for the data? Because one of the things that one of the patterns that I also follow is that all methods that act on an object of type, let's say I have a type struct MCP4461, anything that acts on a structure of that type is prefixed with the name of the type. So it's going to be MCP4461 underscore something. So anything that, any method that is called MCP4461 underscore something, I know that that method operates on an MCP4461 object. And so the code in general, throughout the whole application, the code becomes much easier to read as well. So when we put it into hierarchical containment, then we have all the related variables grouped in structs. We can also have structs inlined. So we can have, if we have a one structure that is really big structure, like the application itself, it has all the data that is relevant for the application. We can actually group things together in that structure using inline structs. We don't have to give our structs any name. We can just group things together so that they become an inline structure. So for example, here we can have a struct that doesn't have any name, and it's called LSS. So everything that is related to the LSS functionality of CanOpen is contained inside this struct. And then I can have, so I have a local scope for anything that's related to the LSS state machine. And the same thing with other parts. For example, we have a request here. It's directly defined as a request directly inside this structure. So you can group things like this into a tree layout to make things even easier to read. If you were to define all of this as global variables, they will just be on a global scope. So not only would they be visible, not only will they be not in a tree structure, but they also would be visible probably by the rest of your application, unless you define them as static, of course. Lower level objects are then going to be defined as objects inside your struct. So you have struct CanOpen counters that keep tracks of all the counters. You have a can listener is a listener for the CAN bus that's going to receive events from the CAN bus. There is also an object for the register map range. So if you work with CanOpen, you have a range of registers that you can read through the CAN bus and also from your application. So you need to have a unified way of accessing them, so you can access them both from the, so that the devices on the CAN bus can access them and your application can access them as well. So that was the hierarchical containment. And moving on to opaque objects. This is useful if you're coding things like things that are dependent on particular architecture. So for example, if you have a STM32 UART, which is dependent on the STM32 library, but let's say you don't want your code to depend on that library at all. You don't even want it to include the STM32 files. So you want to just limit the STM32 definitions into the local file, the local C file of the UART driver. And you can achieve that by using opaque objects. So basically, opaque object is just a pointer. So in C, you can define a structure. You can define a structure locally in your C file, but externally, you can define a pointer to that structure. And because a pointer is just a memory address, the rest of the code doesn't need to know exact layout of that structure, because it's not going to be accessing any variables in that structure. It's just going to be passing around the pointer to that structure. So if you just define a pointer, if you just define the struct, the name of the struct without any content in your C file, then you can pass that struct as a pointer to functions, but you won't be able to access any data inside that struct. And to do that, you don't need to include any definitions for any variables that you have inside that structure. So one example is, for example, the console driver. So we have the console defined locally as a struct console, and then it has anything that is local to the console. And this structure is not visible outside of the console. The only thing that's visible is an interface to the console. So it's going to be console add command, and that's what's going to be then passed to all the other parts of the application, so that they can add commands to the console, but they don't need to know about the actual implementation of the console. So when we work with opaque objects, you would be typically allocating them on the heap, because you're allocating them inside the C file, which creates the object. So you'll be creating an instance of that object on the heap, and then you will be passing around the pointer to the object, because you can't have references to opaque objects. They can only be accessed through pointers. So they kind of have to go on the heap, because you can't define an opaque object as a as an instance. Then we actually come to one of the most useful patterns, which is the container off pattern. How many have seen the container off pattern before?
I've seen it in the Linux kernel source code. It's used most of the times.
Exactly, that's true. That's
And
actually where it comes from. Most of the time.
the one basic use which I saw was using the linked list structure, which is defined in the Linux kernel. So they use, actually they pass only the uh, a pointer to the list. There's this list node inside the structure. They pass the pointer to it. But if you want to extract the data, you use this container of pointer and then get the parent structure, and then you can get the data.
Exactly. That's a very good explanation. And container off comes in for one very, very specific reason. So because in C you don't have you don't have virtual methods like you have in C++. C++ has kind of implemented a lot of those things as part of the language. But there was a need after C was invented, like a long time after C was invented, there was a need to have objects that could be polymorphic. And what do we mean by that is that we have an object that has that we have an interface to an object with a set of behaviors, but we can have different implementations of those behaviors. And one example is, for instance, a serial device where you can have different implementations of a serial port. You can even have a serial port that is connected over SPI to your chip, and then that should behave as a serial port. So you should be able to pass that UART to other parts of your application without having to care that this is a UART connected over SPI. So you need to have an abstract interface. And the C language doesn't have a built-in way to define abstract interfaces. So what they have invented in Linux, which is they invented this because they wanted to have an abstract way of putting things into lists, which you mentioned there. That this is very often used in linked lists, and they wanted to have a generic way of handling different objects. And so one way to do this in C is that you have your for example, if we take the list as an example, it's a simple example, so I can cover that here first. If you have a list described by forward and backward pointers, so you have two pointers that describe your next and your previous item on the list. And so every item has two pointers, one to the next item, one to the previous item. If the list has 0 length, then they're both the same. If the list is longer, then you can either have a circular list or you can have a null pointer that signifies that the list is finished, that you have stopped traversing the list. But you have this structure with two pointers, forward and backward. And now you want to arrange arbitrary data structures into lists. So how do you do that in C? How do you do that in a way that doesn't require you to have like some intrusive, that doesn't require you to write specific list implementations for every kind of object that you want to put into list? The solution to that is using the container off. And what container off does is just provide you with a type-safe way of going back, going from the contained. Let's say we have a serial port here. We have a pointer to a serial port, to this item here, serial port, and we want to get the pointer to the console item, the containing structure. So we're going to call container off, and the first argument to container off is going to be the pointer to the serial port item. The second argument is going to be the type of the containing type. So it's going to be the struct console, and the member is going to be serial. So because the serial is a member here, it's going to be supplied as serial here. And so what this macro will do is essentially go back from the pointer to the member to the pointer of the console. And as a return value here, you're going to get the pointer to the containing data structure. It's not just useful for lists. So it's very useful for aggregating things into lists and just having a generic data structure in C. But it's not just useful for that. It's also useful for implementing abstract interfaces. This is also an idea that comes from Linux. Linux uses this a lot, and all of the device drivers are using container auth to implement abstract interfaces. And they do so in a very type-safe way. So it's really foolproof. Like it's designed in a way that you can only get, like, unless there is a memory corruption or something really weird going on, you will always have the correct pointer passed through your virtual methods. So in comparison to, for example, using void pointers for implementing these types of abstractions, where you then cast the void pointer to something else, this is like light years ahead, because this is completely type safe. This doesn't let you pass pointers of the wrong type if you implement this correctly. So let's, as an example, let's look at the serial driver. So we have a serial driver, and it needs to implement an abstract interface called serial port. The abstract interface has two methods, read and write. So anything that is a serial port has two operations you can do on it, like it's two behaviors, just read and write. And it doesn't matter where it, or at least it shouldn't matter in your application, what type of actual implementation you have underneath. So you want to implement read and write. But how do you actually implement it then? Well, you use container auth. And in the most practical sense, if we look at the definition of the actual implementation here, we define first a structure of function pointers, which is going to hold our virtual methods for a serial port. So anything that implements a serial port is going to have to implement those two methods. And it's going to have to define the structure as a static const. So it's a constant data. It's set at compile time. It's always the same. And we're going to be we're going to be taking a pointer of this interface, and we're going to store it in our actual instance of the object. So the reason we have a pointer-to-pointer situation here is because we want to be able to instantiate our serial port objects, but while at the same time not have to have the whole interface duplicated in every single one of them. So we define the interface as a constant, so that it's the same for all of them. And then inside our serial port, inside our UART here, we have a struct serial device dev, and dev then has one of the structures called serial device ops, which is then pointing to serial device ops for that particular, for the UART device or instance of the UART device. When we then want to access our serial port, we use a pointer, we define a pointer-to-pointer serial port T, and we use this as a handle that we pass around our application. So whenever our application wants to read from a serial port, it's just going to call serial read, and it's going to pass serial port T, a type, serial port T port. It's going to pass that into the method that is actually then defined in a dereferenced version of this handle. So we're using it as a handle, and at the same time, we're also using it as the interface itself. So we're going to dereference it once, then we call the read method, which is a constant set here, and we then pass the handle to that read method. And so what we get when we get to the actual read or write, so it's basically the same definition. We have a write method here on the screen, so we can look at the write method instead. So when we get to the actual virtual method, all we have to do is just call container auth, and we pass the pointer to our handle, or our handle that we got here. So we got it from the call from the user. And we then convert it. We know that this pointer is pointing to an internal structure in our device, which is stored as dev.ops. So we can have dots in this when we pass the last argument to container off, we can have dots there. So if we have multiple levels of structures, that's also accessible when you use container off. And we tell it then that our pointer to, that our serial variable here is a pointer to DevOps here. And we want to get the pointer to struct STM32 UART. And we have our variable called serial, which we got there. And then as a result, we get our local data for the STM32 UART. In reality, it's not that much to write. You just have to sort of get into this habit of using the pattern. So it's a little bit complex. It's one of those more complex patterns, but it's actually pretty simple when you get into the habit of using it. Does everybody have kind of a good overview of this pattern by now? If anybody has any questions, now is the time to ask them. So just unmute yourself and ask a question. So
I have a.
Can you see my screen, by the way?
Yes, I have a question, Martin.
Yeah.
When you declare the structures, do you typically declare them globally, or you declare them within the function and then use it instantiated right away?
How do you mean?
So you said that usually you don't want to have global structures. So by not wanting to have global structures, you meant not wanting their definitions globally, or you meant that you don't even declare them in, for example, a header and use it in other files?
You can have them globally. It's when it comes to things that are very local, like when it comes to device drivers, I don't even declare them globally. So I just have globally, I only have the abstract interfaces for devices. So that pattern works well for device drivers. But it's when it comes to like generic structures, it kind of depends on what type of object it is. If it's something like maybe like a dictionary, let's say a dictionary or a list, this is a structure that is used as an instance often. So you want to have a global definition of that structure. But if you have something that is very specific to, let's say, a particular architecture like STM32, then those things you would try to limit to a particular set of files and not have it included globally.
Okay, makes sense. One more question, not related to this, but in the initial slides you mentioned about the BSS section that is zeroed out. I wanted to ask who is supposed to do that? Is the vendor's startup code supposed to do that usually, or is it our user code that is responsible for that?
That is done in the startup code, and if you include the startup code yourself, then you do that in your startup code. So, for example, in STM32 we have. Let's go to.
That's where I was going. Basically, in Kyle Microvision project, if you include the startup file, then I don't see the BSS initialization here.
Yeah, here is the BSS initialization. It's right after the reset vector. So directly in the reset vector, you have a little bit of assembly code, or sometimes it's C code. You can write it in C as well. But this is kind of what you mean by vendor initialization startup code. So this is directly from STM32 libraries. And in the reset vector, the first thing it does is copy the data and then zero BSS.
Okay, the one I have, it doesn't have it. My startup file is for STM32F207, and it does not have all this part that you have highlighted here for some reason.
So maybe you have like at least the data. You should be copying the data. You could have like the RAM automatically reset to zeros, in which case you don't need to zero BSS because it's going to be zeros. But when you have this code, it kind of makes sure that that you always have a known state, so you don't have to rely on the hardware working a certain way, or you know. But when it comes to data, you should have some code at least that copies data from flash into RAM so that you can access the data and modify it. You know. So it could be either it's done somewhere else in the code in the startup, or you have to do it yourself.
Okay. Okay. Then it's not a good idea to just assume that it's going to be done all with you. We need to actually take a look at the startup to make sure that it's done.
Well, yeah. Like I would always expect it to be there, but you would easily notice, because if you don't have the data initialization, your application wouldn't even run, because you wouldn't have any initialized data. Like all the values that you have initialized to defaults, they're not going to be working correctly. So that part you're going to notice really quickly. It's trickier with data that is uninitialized. So you'd notice that when you start using uninitialized data, and maybe you have some code that uses an uninitialized variable, and you haven't enabled compiler flags to warn you of uninitialized variables when you use them without initializing them. And then you would have different behavior every time, because you're using a variable that hasn't been initialized. Because by default, C doesn't guarantee any initialization values for uninitialized data. So they can be anything.
Oh, okay, that's what I wanted to hear. I wanted to know that this is not like a C standard or something, that this always has to happen like this, right?
No, it's not a standard.
Okay. So where do we get these guidelines? Like you said, the BSS has to be zeroed out. How did we come up with this conclusion?
It's kind of in exactly the same way as when you initialize your objects, you always zero out the memory. If you're allocating it from the heap, for example, it's just to have a known state, to eliminate any kind of unknown or random behavior. Because you always kind of, you just want to have the memory zeroed out, because that gives you a known state. You know.
Sounds good. Thank you.
Yeah.
Yeah, Martin.
Yeah.
Yeah, you were saying these .s files are initially updated, right? These are in boot up time, right?
Which one?
You are showing some code, right? .s that BSS part.
You mean the startup code?
Yeah, this one only.
Yeah.
These values are set at boot up time, right?
This is the code. This is the first code that runs on the chip. So when the chip boots, it will load the address of the reset handler, and it will also load the address of the initial stack pointer. And this is the first thing that will run after reset. So this is the code that basically just prepares the memory, and then it calls system init, which starts up the PLL and the clock and the rest of the system. And then it calls main.
Yeah, normally these values are stored in .h files, right? Header files.
In the what?
In header files, right? Normally these values.
Well, which values do you mean? Do you mean the values for that go into the sections?
Not sections exactly. We need to set some of the values, like we have one project it is multimedia project. In that they set some of the PLL clocks like this. All these parameters are set in .h files.
Okay, yeah, that can be a case sometimes. It doesn't have to be the case. It depends on how the vendor code is written. So in STM32, you have, for example, the HEC value, which is a define that you pass when you compile your code, which sets the value of the external clock. but you don't have to have it that way. You can configure it through your application, through a configuration variable somewhere in your application. But then you have to rewrite the basic vendor code that sets up the initial PLL to make that work. So if your vendor code expects things to be configured in header files, and you have to define certain preprocessor macros to set configuration values, then that's the way you're going to be doing that in the header files. But that is very implementation specific for particular chip and for particular manufacturer, depending on how they do it.
Yeah. You said that ELF format, right?
Sorry, what?
Executable and linkable format, right? ELF format.
Yeah.
Starting slides.
Linkable format.
Yeah. How
That's
to see
the
that?
output of the compiler.
Yeah. How to see that format?
How to see what?
If we compile one C file, right, we got one executable file, right? A.out.
Yeah, if you just compile a C file, you get an object file. It's not a finally linked application. It's a compiled code, but it still needs to be linked.
We cannot see that A.out file, right?
What do you want to see?
You want to see the out file.
Inside that A.out. Yeah. What are the parameters are there?
You can use, for example, nm utility to read. You can use readelf as well. But if you want, what do you want to read from the file? Do you want to look at the sizes of different variables? Do you want to look at what's in there, what's contained?
No. You said ELF file formats having .bss or .ro data is right?
Yeah.
Yeah. If I want to compile one C file, I will get one A.out, right? By using some obj dump file, obj dump tool.
Yeah, if you use the obj dump tool, then you are dumping the sections into binary format or hex format, for example. But you're taking the well, you can dump the contents of the both objects and ELF files. But what are you trying to do more precisely? Like, do you want to?
I think he's asking for the intermediate file, which is A.out, or the file that preprocessor outputs. But I think that gets deleted after the compilation is completed, if I'm not wrong.
Well,
yeah. How to see that all these files, .ro files, how much memory it will use? Which register it will use? Just .txt, .text, .bss is there, right?
You can use the size utility to get the size of the sections. You can also get the size of the sections by using.
No, I am not concentrated on size. I need to know that registers and BSS part, .ro part.
Do you want to see? Do you want to make sure that all the data is there?
Yeah.
Okay, you can check. You could use the nm utility to check for everything that's included, all the symbols that are included into the file.
Okay.
Would that solve your problem?
Okay. And
yeah,
one
or
more
you
thing.
can take a look at the map file too.
Yeah, the map file, that's a good, but you have to generate it though. So you have to add the linker directive to generate the map file.
Okay. And one more thing, we in drivers we use a static function used right in each function. In drivers,
How do you mean a static? Do you mean init function?
why we use static before each function in drivers? Can you please explain? Here static int serial data is there, right?
I use static because I don't want those methods to be visible outside of the file. So those are, whenever I use static, it basically means that the method is local to the file. So it's not going to be a symbol that's visible from outside of the file.
Okay.
And you could do you could declare everything as static. So in a lot of in the drivers that you write with abstract interfaces, nothing needs to be exported. So not even the driver data structure needs to be exported from the file. So it creates a really encapsulated design where you're just registering your devices, and then you are accessing them from your application through abstract interfaces. But you don't need to even have the methods declared outside of the file. You're just using the abstract interface to access the functionality of each instance of each device.
Okay. Okay. Thank you very much, Martin.
You're welcome.
Hey Martin, Pradna here.
Hello, Pranay.
Hey, so I have a doubt about ELFL. Sorry, I joined a bit late. I read about it and I tried to dig up more into it. So I just want to know what are the advantage or the benefits it does give. Like, is it just used while linking and loading? Is it all about taking the section parts from the ELF from the this ELF file and load into respective section in the memory? Like code should go to text should go to text, and then stack should means the local variable should declare in the stack. And likewise, is it the only advantage over the normal binary?
Well, the ELF file is the biggest advantage is that it's supported pretty much everywhere. Like even if, for example, if you're compiling something that you're going to load using a bootloader, you're going to be you're going to tell the bootloader where your application is, and your application is going to be contained in the ELF file, and then the bootloader will load each section where it has to go in memory, and then it will run your application. And also, when you're working with all the GCC tools, they are natively work with ELF files. So everything around the bin utils for working with binaries, it's using the ELF file as a standard container for everything. So it's a good intermediate format for compiling your application. You compile it to an ELF file. It's stored in that container with all the symbol information and debugging information that you might have in the ELF file. And then when it comes to, if you want to just flash it directly into the flash memory of the microcontroller, then you convert it into binary file. But you still have the ELF file because you want to have access to the debug symbols of the application. So when you then load your application in the debugger, you load the ELF file with all the debugging information, and you connect to your microcontroller over JTAG with your debugging tool, and you can read out the position of your current program execution, and then you can your debugger will basically look into the ELF file to see which symbol is at that location. So the ELF file is always usable. It's used, like you can use it to check how big is your data section, how what symbols you have in your application, to make sure that you don't include too much code. Like maybe you're compiling a lot of code, but you want to make sure that your firmware is as small as possible. So anything that you're not using should be excluded. Then you can use the NM tool to and run it on the final executable to check what is included in your executable. And you can also check the sizes of every single variable, and not just variable, but also every single function. You can check the sizes of those symbols through the NM utility that reads the ELF files. So the ELF file contains so much information about your program. It's a container format, but it is the ultimate kind of container for executable files, I would say, because it's really flexible, and it's used on all the Linux systems.
Okay, when you're saying this debugging information, so is it like we have to enable some sort of level of debuggings, and that way that code will come into the picture of the ELF, and that's how we will see? Is that so?
Yes, you need to enable the G option at the very least to include debugging information.
Okay. Thank you.
So when you compile your code with the G option, so you have to enable the G option for every single compilation unit. So you have to then recompile your whole application, and every single C file needs to be compiled with the G option. And when you then link everything into a single executable, the ELF file, then all the debug information is going to be there because you have included that information.
So does .config file have any kind of other certain variable to check in for that? Like, I mean, do we have anything, any macro in the .config files?
Which .config file do you mean?
So whenever we compile Linux for any of the target, at the end of the compilation, we get the .config file where we have respective configuration for the hardware.
Okay,
That
I'm not familiar with, I'm not using any .config file, but I'm guessing that maybe that's the compilation options that you have used. Maybe your IDE is generating that, right?
yeah.
Basically, those options are basically for including all the drivers and everything. Basically, Linux supports a lot of different drivers and a lot of different things. So basically, if you are compiling Linux for a Raspberry Pi, and if
Oh,
you are
you
compiling
mean
it,
the menu the output of menu config? Is
yeah,
that
yeah,
what you mean? Yeah,
Yeah,
right.
I
yeah,
think
yeah.
Yeah. So that's a config for the options that you want to include in your kernel. But those are basically like they enable and disable certain preprocessor directives in the code. So when the code is when you run menu config, it also generates a config.h file, which contains preprocessor directives. And so in your code, you can then conditionally include or exclude different parts of the code. And also you get directives for the make files generated as well. So you can conditionally include complete C files into your application as well. So what was your question about the config file? How do you?
Yeah, so I wanted to know, actually, we have couple of debugging option there also. So the way we are enabling half ng, I never tried to traverse, just wondering to know. It's totally fine. Like, do we have any level-wise debugging option there also, if you have ever come across?
Oh, I almost have to check then what options would
uh,
be available there. But
I
there are
guess
quite a few options for debugging besides just the normal debugging information.
also in the make menu config there is a specific tab for kernel hacking, and that enables a lot of debugging options.
Yeah.
So basically, it's called kernel hacking.
Oh, okay. Thanks, Purajan. And yeah, another down, I'll just finish quickly. In the reset handler function that you showed, generally the reset handler starts with disabling the interrupt. So far, miss, I just read about it, but the reset handler function that you showed for STM32, I couldn't see disabling interrupt over there.
They are disabled by default, I believe.
Okay.
I would assume that if disabled by default because you then enable things. You start the clocks and you enable things. But I would have to check the data sheet, but I think it's designed in a way that you don't actually need to do that.
Okay.
Because you don't have any interrupts coming through to your handlers when you start. So the nested interrupt controller needs to be configured to let through the interrupts. And also you need to configure interrupts on every peripheral to trigger interrupts. So when you're reset, I'd have to check the data sheet to know 100%, but my wild guess would be that nothing is going to go through until you enable it.
Okay. Okay. Thanks a lot, Martin.
Right.
Please proceed. Yeah. Thank you.
Any other questions?
I have one question, Martin. Yeah, you said like we are not going to use global data or something like that. I mean, it is. I mean, where we should not use global data. Like, for example, is it in the case of drivers, or is it in the case of application?
Nowhere. I would say just nowhere, because it violates the basic premise of data flow through your code. Any global data makes your code both more difficult to read and also more difficult for you to understand what side effects it might have. So you wanna keep the data flow through the code and not outside of the code. So in practice, you never have to use it. it doesn't matter if C language allows you to define global things. You don't have to use it.
Okay, so for example, like in the case of some variables, like global variables, which we do define. So what about them?
So give me some example.
What can I say?
Interrupt registers.
Yeah,
We
something
use,
like that, and addresses of the
yeah,
particular interrupts.
Yeah,
we
so
use
the registers are the only thing, as I said earlier as well. Those are sort of the globals that define the registers and global fixed addresses. Those are the only things that make sense to make global, because you have to. There's no other way, right? But when it comes to anything else, you don't need to make it global.
multi-threading also we use.
So what do you need to define globally there?
So, okay, you mean to say like the address of the particular registers and everything we can define globally?
Well, if you have things like, for example, the type defs that define the register ranges for, I mean, you don't even have to define that globally, right? But the way that STD peripheral library is written is that you have those addresses generated and they are global. So when you access like UART1 and then arrow DR to access the data register, that is a global variable. But you don't have to define those as global either. For example, it depends how you handle your configuration, but if you have everything in a device tree, for example, then you no longer have that as global either. It's just that you get your register range into your device driver, and then you just configure a local variable inside your device driver structure that holds that base, the base of registers for the UART. And then you access the registers through that variable. So that's not global anymore either. Really, like, there is no reason for having anything global.
Well, what about the functions where, for example, you have a software counter or a timer that you increment in an interrupt, but then you don't want to hold up the interrupt performing all the tasks. So you go back to your main loop and you see if the counter has reached that value. So in that case, what do you say? What should that variable be global or not? Or in other cases, when you have like an interrupt function that you don't want to hold up too much time in the interrupt, you set some flags and then go back to the main loop, and then perform functions on that based on that flag.
So I would say with interrupts, nothing should be global outside of the file. So you want to avoid situations where you are either calling a function from the interrupt that is outside of your file, so you don't know, in that function, you will never know that you're being called from an interrupt. Or when it comes to variables as well. So what you want to do with interrupts is keep it local to the file, and have you can have a variable that is local to the file. It's defined globally because you have to, because you have an interrupt handler that is global, right? So you have a variable in the file, but it's static, so it's not globally visible. And then you have a function for accessing that variable that disables the interrupt, because you have to disable interrupt to access it. If it's a counter, you're incrementing from the interrupt. So you have an extra function that disables the interrupt and reads that variable and returns it. But you can have that and operate on an instance as well. But it's kind of like you can have a dummy instance just for the sake of keeping things consistent across the application. But when it comes to interrupts, those are global functions. So you have to kind of have a little shim there inside the same file where you have a global variable through which you access an instance that is responsible for a particular peripheral that interrupt belongs to. So I can show you an example. I think it's easier to.
Yeah, that'll be great.
Yeah. okay, we can look at the UART devices. So we have a UART structure that represents the UART device. So this contains everything that is relevant for a UART, right? And we have to have a number of structures here that represent the UARTs, because the interrupts because we have a number of physical UARTs that basically are on the chip. So we define a number of UARTs here. But then whenever the application needs to create a UART, we basically just place a pointer here so that we have that UART accessible from the interrupts. And we have then a handler. So here's the default handlers for the UARTs, for all the different UARTs. But then they call the same code that handles the interrupt regardless of which UART it is, right? So because I have made this into a struct here, that is a generic structure that represents a UART, and it has a variable HW there that points to a particular register range for the UART. I can then just use the same code and reuse the same code regardless of which UART it is. And to the application, this looks just like an abstract instance of a serial interface. So when I have the startup, when this thing starts, it will instantiate an instance for every single UART that is being used in the application, and then it will just registers those UARTs with the serial interface, so that then the rest of the application can use them as a generic type of serial interface. So you have to have this number of pointers here to structures that are global. They're not global in the sense that they're global throughout the application, but they're just global inside this file. But then everything else can be done through an instance of an object. And one thing that you mentioned there with a counter that you increment in an interrupt and then you use it somewhere else in your application, you want to avoid that kind of thing, because now you have a counter that can be, you can be accessing that counter. You never kind of know if the value is consistent, because you're trying to access it directly and it gets updated from an interrupt. So you have to always make sure that you disable that interrupt that updates that counter. And you can't easily—
you set it as volatile.
Yeah.
You typically set it as volatile if you're going to use it in both functions. So it should be up to date all the time when you read it, right?
So you're going to be reading the counter from anywhere in your application.
Yes, but you declare it or define it as a volatile variable, so that the compiler doesn't optimize it and it does not copy it into registers or any other place. So it only has one.
You know, it so happens that on ARM you have kind of a guarantee in it's kind of a guarantee that integers that are 32-bit are going to be written atomically. But just because you declare it volatile, volatile simply means that the value can change. So in your code, if you're reading that variable once and then you read it again a few lines down, the compiler will not optimize those two reads into one. So it's going to read it twice, right? So that's what volatile gives you. It doesn't give you any safety with respect to interrupts. So it simply tells the compiler to read it twice if you're reading it. So if there is an opportunity to optimize it into a single read, the compiler will not do that if it's a volatile variable. But beyond that, it doesn't give you any guarantee that you're accessing it atomically. Besides the fact that on ARM, like if you're coding ARM Cortex, you kind of know that integer accesses should be atomic, but it's not a 100% guarantee. You still should be using synchronization, and you still should be disabling an interrupt when you access a variable that is shared between interrupt and your application. So you kind of still have to take care of that to make sure that you don't get weird bugs that you don't know what's going on there.
Cool.
So it might work on ARM, and then if you use the same approach somewhere else, it won't work anymore because now you don't have an atomic access to 32-bit integer, right? So that's the kind of problem you get.
So Martin, while compiling this code, if something goes wrong here, then at which state do we really know? Like there, I could see there are quite few UART support. So if any of one is like maybe one is applicable and something, I'm trying to say if any of the device on the SoC is not working, how would we know?
Well,
Maybe
that's
a
good.
GPIO or a LED?
If any of the device is not working, do you mean during its initialization?
Yeah.
Well, in this case, it's going to fail in initialization. It's gonna print out an error because this is a bare metal firmware that I'm using on a Crane controller. So I use it as example here. And if it fails to initialize any device, it's going to print out an error. So it's going to be very.
Also,
And it's
I
just,
guess that will be runtime error, right?
yeah, that would be a runtime error based on the fact that it cannot initialize the device for whatever reason.
Okay. Okay.
And it has to be a runtime error because you don't know ahead of time whether everything is connected properly.
Yeah. Yeah.
Like with UARTs, it's easy, but if you have something on I2C bus, maybe some revision of the board doesn't have that device, so you kind of have to probe that. So that will be done at runtime.
Okay.
So is this clear to everybody? The abstract interface stuff?
Yes.
Okay, cool. So now we get into a few other higher level patterns here. When it comes to working, we started talking a little bit about this, like working with interrupts. How do we pass data back and forth? How do we make sure that we do it safely when we work with interrupts? And I'm going to talk a little bit about that. So interrupt patterns are designed to kind of give you the fast response to hardware events, but also you want to make sure that because the problem that you get when you just work directly with interrupts is that you would run into a problem when you need to do something more than just toggling some flag and reading out data from memory that's already on chip. If you need to do some I/O that can take some time, you can't do that directly from an interrupt. So you need to have a better way of doing that. And the concept that we have invented in computer science since a very long time ago is the scheduler that enforces time. So the main purpose of the scheduler is to enforce time. And the way that you do this, combine this with interrupts to handle interrupts, is that you have something that is called threaded interrupts. So you defer some of the work from the interrupt into a thread that then does the complicated I/O that needs to be done. And the thread can then sleep and do things that can take considerable time to complete, while the interrupt just exits, and then the application can continue and other interrupts can happen as well. So let's see here. So we will get to the deferred work pattern there. We can start with the task pattern. So the task pattern. So when should you be using an Artos, and when should you be okay with like a bare metal application? That's the question that arises. When should you be switching to an Artos, and when not? So to understand how to make this decision, you have to understand what Artos is basically, what is the function of an Artos, and it's to enforce timing. That's the only thing that it does. It's a mechanism to enforce timing. And the way you do it is by forcing a task to stop running when something else needs to be done, and when the task is taking too long time to complete. So it's fairly quickly, like whenever you work with something that, like whenever you work on microcontrollers, you pretty quickly run into this problem that you do need to make sure that things finish in a certain amount of time. And you kind of want to make sure that certain tasks or certain things run at periodic periods that are pretty much the same every single time. And then when you have a lot of things that need to be happening at different times, things get really messy. So now you have a main loop that counts on some counter, and depending on the count of that counter, it will do different things. And neither of these things can be guaranteed to complete on time. So then you start using a watchdog maybe, and you have to reset the chip if things take too long time. So what is the solution? Well, you switch to an Artos. That's the solution, because that's how you enforce timing. So you split things up into different tasks. And the way that I like to explain it is that you want to group things based on time domains. So you have different time domains. For example, if we consider a console that reads user input and it does something in response to the commands. It has a very slow, it has a very slow time, how do we put it? Like a heartbeat of that task is very slow. Like user presses a key, that's an event, it puts that into buffer, user presses enter, it processes the buffer, executes some commands, and then prints out the result. So that's a console. And that's a isolated application. You don't want to have that as part of your main loop. Like you don't want to mix things together with other things that are related to the console. You probably want to have a console as a separate application, isolated and just running by itself, and running its little loop that involves reading the input, sleeping on the user input, and then whenever user presses enter, it's going to run something and then go back to sleep again. So that's one domain. And in an application, you have usually several of these domains. So there are things that happen at different heartbeats. Your controller might have its own heartbeat at 1 millisecond. So maybe you're running things every single millisecond. You have to run your control loop and calculate your new value for the actuators. So that would be its own little time domain. And then you might have something that takes a long time to finish, like to read. Let's say you have a ultrasonic sensor that needs to send out an echo, and then you have to wait for the echo to come back, and then you have to interpret the timing in between there. So considering that maybe you're not using hardware timer for that, but you're actually doing that in software, that's a separate time domain. So that's going to be a 20 millisecond period. That's the 20 millisecond heartbeat for that task. And it's very quickly that you can identify those different time domains, the things that happen at different heartbeats. And those are the things that you put into different tasks. So when you split things into tasks, you try to group things based on their timing, because the main purpose of the Artos is to enforce timing. That's what it's designed for. And so splitting things up like that and running an Artos opens up for utilizing the CPU to the maximum, because now you can put things to sleep whenever you are waiting for I/O to happen. So the scheduler gives you that functionality. So now whenever you have let's say you're sending out a command and then you're waiting for a response from some device, and you can actually put your application to sleep during that time and not do anything and just let the interrupt happen. And then from the interrupt, you might get some event coming up into a queue that your current task is waiting on. And then the Artos will wake up your task, and then you can process the data that has just arrived. So you can now slice things up into more than just the time slices that you use for Artos scheduling. You can slice things up into even greater level of detail, where you can switch between tasks really quickly, depending on what events are happening when. So you get really responsive system. You get really good CPU utilization. You can put the CPU to sleep whenever you're not doing anything. So you have, there's really like, you should be using Artos whenever you can use an Artos. There's really no reason not to use an Artos from the beginning, unless you're on a really, really small microcontroller that where you don't have enough memory to use any kind of Artos. So that's the task pattern. And for example, we have an indicator loop that just the whole purpose of the indicator loop is just to indicate things on LEDs and depending on the state of the application. That has its own little time domain. It's an isolated thing. It can just run by itself and not worry about anything else. And then you have the control loop that does all the measurement aggregation, updating the state, updating the control, updating the motors. And that's a high priority task. It has to be run at exactly the same time every single time. And so that will be a separate task that is placed at the highest priority, and it always has to run and meet its deadlines. So it doesn't matter if the indicator task is preempted at any point in time, but this task on the left, it should never be, it should never miss its deadlines. But the place where you get more use out of the splitting things up into tasks is when it comes to communicating with interrupts, because as I said, when you have a situation where you need to read something and it takes time, you want to defer that work. And so we have a pattern where we defer work from the interrupt into a thread that then handles that work. And the simplest example here is just even just having a UART that is interrupt based, and it pushes data that arrives on the data register into a queue, which is then read by another task. So you have an interrupt happening, and it has to read data quickly, read it out, then place it on a queue, and then the data waits there until a task reads the queue. And then if a task tries to read the queue, and let's say it decides that it can wait a little while for the data to arrive, then the task is put to sleep, and something else can run until an interrupt happens, and the interrupt will push data on this queue. And then if you use, for example, in FreeRTOS, if you yield from that interrupt, you can actually switch to the task directly. So you switch to the task within 20 microseconds. It's a really short period there. And you can just run the task directly and process that data. So whenever new data arrives. So this gives a very flexible way of avoiding doing too much inside an interrupt. So you can exit the interrupt, go into task context, and then run it at the priority of the driver task that is responsible for handling those interrupts. So very useful. And I showed a little bit of this when I went into the UART example, where we push things, push the data into a queue, and then application reads that from the queue. But you can also have a situation where you wanna kind of cache the state of the device. So let's say it takes a while to read registers on the device. So you want to keep registers locally, and then have single updates to the device. So you would be making reads. Maybe you're doing multiple reads from the application. Let's say maybe it's a sensor value that the application wants to read, and you'd be updating that value at regular intervals. But to the application, you would be giving out a cached value and maybe an interpolated value as well. So it depends on the implementation that you want to have. But here you're kind of you're having a task that accesses the hardware at regular intervals, but then to the application there is a no wait situation. So you don't wait for new data to arrive. You just calculate the value and give it away to the application. So that's an instant read for the application. So that's useful because you might have many reads, and especially if you want to make sure that your application can always get the latest or the latest maybe interpolated value right away without having to wait. So if you have a main loop that needs to finish in a certain amount of time, and you can't afford to wait for the I2C device to do the read, because that might take longer time than you can handle, but you can you can handle a slightly inexact interpolated value as long as you get it at every single iteration of your loop. So then you would use a caching pattern where you cache this data in memory. And the same thing for switches, where we basically handle the state of the buttons. And the aggregator pattern, I'm just mentioning it sort of as I showed with the main application, where we just aggregate all the data together into one big object that contains a bunch of smaller objects, like this. So in the application, we just have a bunch of abstract interfaces for different devices and instances of those devices. So that's it.
I have a doubt.
Sorry, go ahead.
So when we transfer the data from the kernel space to user space, why do we use always copy operation? Don't you think moving can free the more space in the kernel and we can use huge space?
Well,
Like,
you have
why
to.
is there copy? Is there?
Well, you have to copy it into the address space of the process. That's the main thing.
Okay, yeah, miss. The data we are copying, not moving.
So can you give an example? What are you working with?
Okay. I'm not working as so specific, but yeah, when we have to read a data from any of the sensor, interrupt trigger the handler reads the data for us, and we copy that data from maybe copy to user using copy to user or some other function. We have the data in the buffer that we created in the kernel space, and then we for the application to read it, that data should move into the user space, right?
Well, yeah, because you would be providing a buffer for that data. So when the user executes the read system call, it's going to provide a buffer where you want to put the data. So you're going to be basically moving that data to that buffer, which is provided by the user. So the buffer where you are placing the data is provided by the user, but you can't take that buffer and use it as is for internal. Like when you don't pass that to a DMA peripheral, for example, you just want to keep that separate. So the user provides you with a buffer where you have to put the data, and then you copy that data into that buffer and give it back to the user.
Yeah, so it is always about copy operation. We have the APIs to transfer the data from kernel to user. It's like copy to user, copy from user. It's all about copy.
Yeah.
I'm just wondering, why don't we move the data?
So
Why don't we use move operation?
what is the difference?
Actually,
Like,
move and copy is the
oh,
same thing
somebody
in
has
the.
information there.
So basically, move and copy is the same thing, right? You can't move data because the memory which was there earlier will stay there. So
Yeah, exactly.
just copy the data. And one other question you might have is why to copy the data, why can't I directly access the kernel's data? That is because the address space is different. So you can't directly access memory of the kernel because it is privileged.
Yeah, indeed. Means that's like a valid thing that we have to means we cannot allow any application to use the kernel space data, but we are again copying. Like, I was thinking one reason is multiple file can reach one buffer, so moving maybe one application is using it there, we are using synchronization, and after using, if we are moving it, then other application may not read. So it's like there could be many consumers for one read. I thought that is one main reason for copying the data and not moving. But as you said that copy and move is one and the same, then I guess that can make a sense, but not
So,
100%.
by move, do you
Yeah,
mean that you
Pradya,
copy
there
the
is.
data? By move, do you mean that you copy the data and from where you moved, you can use that for something else? Is that what you mean?
Yeah, once moved, that address won't be having valid data to read.
That can happen, but that depends on the exact application and situation.
Hi, this is Ajay.
Okay.
Raja, there is no movement of data. We using pointers only to store values and free that pointers only. There is no point of moving the addresses like that. We are using a pointers concepts in user space. We are using mloc. In kernel space we use kmloc. We have virtual memory concept is there in kernel. We use just that concept only for storing the data. There is no concept of moving data.
Okay.
So basically, there is a page
Uh,
table that
Yeah.
so
Virtual
there's
memory
this.
concept is there.
So
Sorry to interrupt. Can you repeat it again? Like you said, KMLOC and MLOC. Can you repeat it again?
Me only.
Yeah.
Okay, there is no concept of moving data. We are using the pointers concepts. We need to store the data in pointers, and we are freeing the pointers. In user space, we use mloc, cloc, and real and we free the pointers. In kernel space, we use kmloc, vmloc concepts are there. Using virtual memory concept, we use some base tables concept is there. By using in kernel space we use that memory, so there is no
Okay.
concept of moving data.
Okay. So in kernel space, you mean to say we are using virtual memory?
No, uh, we use physical memory also based on the.
basically, we can't directly use physical memory as far as the 8086 or i3 or all the x86 derivatives are concerned, because paging is already enabled by the hardware. So any address will go through the paging hardware, and then the address will be formed. So if
Yeah,
any ad-
yeah, yeah,
so
I
if a-
agree, but yeah, continue.
so if any address you are using in whatever way, it will go through the page directory and the page table, and then the full address will form. So you can't directly like uh, go to a physical address, because initially the first thing the kernel does is that it sets up the page table and the page directory, and then it allocates some pages for the user process, and then the user process can use only those addresses which are in its page table.
Yeah, I agree, that is the concept of virtual memory, right? You are saying converting
Yes,
physical
yes,
to.
yes,
Yeah,
yes.
yeah, I agree. That concept only I am saying. Basically, we have some of the flags in KML. Like, if we allocate using some flags, it will allocate memory in kernel memory. Some flags are there. Based upon our application, we need to allocate using that flag.
Okay. Thank you, people.
Okay, guys, in about 15 minutes, we got a guy who is part of the core development team of NeoVim joining us. So we have another 15 minutes here. If anybody else has any questions, then go ahead.
Sure, Martin. I have a question, if it's okay,
Sure.
about these device driver patterns.
Yeah.
And if you have a device at the direct memory access, let's say it's filling a buffer somewhere. Is there some of these patterns that's very applicable in that case? I mean, I guess you would still get an interrupt, but you would get it more rarely, like once every time the buffer is half full or something.
Yeah, so if you're using DMA, you will have you can enable interrupt on half full or transfer complete. So half transfer or transfer complete. And if you want to have continuous stream of data, you can actually have a ring buffer. So you set your DMA into ring buffer mode, and then you can be writing and filling out half of the buffer at a time. So whenever you have an interrupt happening at half transfer, you fill out the previous half that just been transmitted with new data. And then at full transfer, you fill out the second half. And then the DMA continues in the beginning. So it's going to be working pretty much the same as with interrupts in general. So from your application, you're going to be providing a buffer that you want to write, and then that will be copied into the DMA buffer as the DMA transfer completes, right? And until all data is copied, and then the driver will release your unblock your application, and your application can continue.
So I was under the impression that in such a situation you would use a shared memory area that you then that the DMA engine is accessing and your user application is accessing.
Well, no, that's a memory dedicated for that buffer. You're not accessing.
Oh, so you copy it out
Yeah.
into your okay.
Yeah.
Very good.
So you have a special buffer set up where you configure the DMA engine to work with that buffer, and then in the interrupt you fill out that buffer as the transfer progresses, right? So you have a dedicated buffer.
Okay.
Has everybody received the invitation for the next meeting? Because that's going to be on a different Zoom URL.
Yeah, I have.
Okay. If anybody hasn't received that, then you can just let me know.
Hey, Martin.
Yeah.
Is there any way to like notify you through messaging or something if somebody is stuck outside? Like last time I got disconnected during the Vim meeting, and I was trying to join back again, but I kept waiting.
Yeah, actually there is Discord server is there. That is what I was saying to some of the members, but they didn't understand. So there is some Discord server which we are keeping. So you are welcome to join in that. So you can share.
Oh, how do you join that?
Yeah, I'll send you one welcome link in the group now.
Okay.
Yeah.
So yeah, everybody should be on a Discord server, and if you cannot rejoin, then just tell somebody who is already has already joined, like Shrikant, for example, and tell them on Discord, and then they can tell me while I'm presenting. Unless I see that on the Discord as well.
Okay. Can somebody share the link for that channel here?
Yeah, of course. Give me a second. I'll be sharing that.
I got a link.
Yeah, I do. Even me too.
Yeah.
Thank you.
Yes.
So we got a few people joining. That's good.
Yeah, I can see them.